starting.
In the last lecture, we proved the recognition theorem for direct products. That was theorem 9 in section 5.4 of Dummett and Foote. And it said, suppose we have a group G and we have two subgroups H and K of G. And they satisfy two conditions. One, that H and K are both normal subgroups of G. And two, H intersect K is the trivial subgroup. Then the internal direct product, HK, which we know is a subgroup of G by the first assumption, is isomorphic to the direct product, H cross K. So in particular, if the internal direct product is all of G, this gives a way to say that G is isomorphic to the direct product of two of its subgroups, H and K. So what I want to do in this first video is talk about applications of this recognition theorem. Let's do the first one. Let's suppose that n is an odd integer, positive integer. We're going to show that D4n, the dihedral group of order 4n, is isomorphic to D2n cross Z mod 2Z. And okay, D4, D2 doesn't really make sense. So let's suppose that n is greater than or equal to 3. Okay, so how do you think about the elements of D4n? Well, there's a nice presentation that we've used quite a lot already, which is it's generated by two elements, R and S, where R is this rotation of order 2n, and S is a reflection of order 2, and RS is SR inverse. We know that every element of D4n can be written as either some rotation r to the I, where I goes from 0 to 2n minus 1, or it can be written as this one reflection S times some rotation r to the I. All right, so we want to apply this recognition theorem for direct products. So we want to find two special subgroups inside of D4n. Let's take H to be the subgroup generated by R squared and S. And let's take K to be the subgroup generated by R to the n. So the first thing we have to do is understand these subgroups a little better. If we want to apply this theorem, we need to know that they're both normal subgroups of G and that their intersection is trivial. And then we have to understand this internal direct product. Okay, so what does this subgroup H look like? I claim that it's isomorphic to D2n. Why is that? Well, think about what H is. It's generated by a rotation. This rotation now, R squared, has order n instead of order 2n. And the same reflection S. So what do the elements of H look like? I'm going to write down 2n elements of H, and you can convince yourself that there really aren't any others. It contains R to the 2i power for all I between 0 and n minus 1. And then it also contains S times R to the 2i for those same values of I. So this is enough to really carefully write down an isomorphism between this group H and the standard presentation of D2n, where you just take R squared to the rotation generating D2n in the standard presentation. All right, so why is this a normal subgroup? Because it has index 2 in D4n. So that makes it normal. We know that every index 2 subgroup is normal. So let's shift gears and look at this subgroup K. K has order 2. So it's not clear that this is normal, but we'll show that it's normal by showing that it's contained in the center. We know that any subgroup of the center of a group is a normal subgroup. And maybe this is clear to you. We've talked a little bit about the center of a dihedral group before, but I'll do this example carefully. So we'll show that it's in the center by showing that the centralizer of R to the n is all of D4n. And we'll do that by showing that the centralizer contains S and the centralizer contains R. So we know the centralizer is, so we know that the centralizer is a subgroup. So if it contains a generating set for D4n, it's going to be all of D4n. All right, so let's just see what we get when we take r to the n times s. Well, that is the same as s times r to the n inverse. Right, so you can check that this really does follow here. So that is s times r to the n, because r to the n inverse is itself. So that means s is in the centralizer of this element. So it's clear that r is in the centralizer because r to the n times r is r times r to the n. They're contained in the same cyclic subgroup generated by r, so they commute with each other. Okay, so that tells us the centralizer is a whole group, or another way to say it is that r to the n is contained in the center of this group. So that means the subgroup generated by r to the n is contained in the center, so it's also normal. Okay, so what have we seen? We've seen we have these two subgroups, H and K, and they are both normal subgroups in G. So what do we want to check? We want to now check that their intersection is trivial. How do you do that? Well, I'll pause and erase and I'll write down the details, but we already have a complete description of the elements of H, so this is quite straightforward. Let's finish our discussion of this example. Since n is odd, r to the n is not equal to r to the 2i for any I between 0 and n minus 1. So r to the n is not in this subgroup H. But the only things in K are the identity and r to the n. So if r to the n is not in H, then it's clear that H intersects K is just the identity. So that tells us already we have two normal subgroups inside of our group, H and K, and they intersect trivially. So we know that the internal direct product, HK, is isomorphic to the direct product, H cross K. But what is the internal direct product? Well, first, how big is it? The size of HK is the product of the size of H times the size of K over the order of the intersection. But this is this is 2n times 2 divided by 1. This is 4n. But D4n also has order D4n. So these two sets must be the same. The internal direct product is all of D4n. So you can also check this directly, that every element in D4n can be written as a product of something in H times something in K, because we have such a nice description of the things that are in H and the things that are in D4n. Now we just apply the recognition theorem, and we know that the internal direct product is the whole group is isomorphic to H cross K, and H is isomorphic to D2n, and K is isomorphic to Z mod 2Z.